Welcome to Q&A Wire.
Okay, so this problem is asking about what happens when a coal power plant, you know, uses all this power, and what's happening to the water, what are the quantities used in the problem, and one kind of complication to this problem is it's all in rates, like it's not like heat, it's heat per second. So you can kind of get around that by just sort of dividing both sides by time in the equation. So you'll see me do that throughout the problem. So anyway, the first part says, what is the rate of heat that's input into the plant? And it gives you the power and it gives you the efficiency. And so we know the formula for efficiency is the work done divided by the heat that goes into some process. And and then this W is, I'm just going to write it out for clarity. So let me go back a little bit because I don't want it to get confused with watts. So I'll write work. Now, if you divide the top and the bottom by time, then you get power. Power is energy per unit time, work per unit time, and Q, and then we have Q hot per unit time. And that's, I think, what we wanted to solve for. So you got Q hot per unit time is, it's the power divided by the efficiency, and then that's 100 megawatts. So 100 times 10 to the 6 divided by 0.4. And you can do that in your head, maybe. And you got 250 times 10 to the 6. Sorry, I didn't mean to be patronizing. So you get 250 times 10 to the 6 joules per second. And I'll put a little box around that. And then for part B, it's asking how much coal is used if the heat of combustion is 2.65 times 10 to the 7 joules per kilogram. So it's just saying that per kilogram of coal, you're going to get 2.65 times 10 to the 7 joules per kilogram. So it's not really like a big physics law that we would use to figure this out. It's almost like kind of a unit conversion in some sense. So first, we want to get the total amount of heat in one day. So first we need to convert the unit of days to seconds. So 1 day is 24 hours. And then that's 3,600 seconds per hour. Hours cancel. And so you got that there is 86,400 seconds in 1 day. So then you can get the heat. So this is a huge number. Is 2.16 times, oops, didn't mean to put the times up there, times 10 to the 13 joules. And I just got that. Oh my God, I keep wanting to write ahead of myself. And I got that by just multiplying this 250 times 10 to the 6 joules per second by 86,400 seconds. And then this is a Q. And great. So then for part C, let me just double check. Oh, whoops, I didn't finish the problem. Sorry, so this is the amount of heat used in 1 day, and then you want to kind of convert that to how many kilograms. So, 1 kilogram per 2.65 times 10 to the 7 joules. And when I did the math, I got 815, basically 815,000 kilograms of coal. So first, okay, So now for C, it's asking about the water dumped into the cold reservoir. Of course, when you use this equation, so 1 minus QC divided by QH. You solve that algebraically for QC. You get QC is QH times 1 minus E. QH is like just this number. So I'm just going to like write. Actually, I'm just going to go back and correct to make sure this is kind of clear. So this is your QH. And then this is really your mass when you actually write this out. Okay, back to part C. Yeah, your efficiency is your 40%. Your QH is that number. And plugging that into a calculator, I obtained that in one day, 1.3 times 10 to the 13 joules is used per day. And then if you want to get the rate, you need to convert days to seconds. So one day, again, is 86,400 seconds. I guess you don't really have to do the conversion. But if you want to put it in terms of watts, then you do, because watts is joules per second. So that's 1.5 times 10 to the 8 watts. Okay, so for part D, it's saying like there's a hot and cold part of the river. What's the mass flow between those two because of the heat flow? So I'm just going to use this Q is MC delta T from a previous chapter. And then so if you consider kind of I zoomed in. No, what happened? Oh, whatever. Okay. If you consider the question, how much heat had to flow to heat up water, that like this would kind of answer it, given that you've heated up the water by, so it's 18 to 18 and a half, so by half a degree C. And so we kind of already know the heat going into this process, and we know the change in temperature because we know it's changed from 18 to 18 and a half. So we can get the mass. We can just solve for the mass, and algebraically then you get mass is Q cold divided by C delta T. And then as I referenced in the beginning of the book or in the problem, we can just divide by T on both sides. And then now we have like a mass per unit time coming from the fact that it's like a heat per unit time. So we said the heat per unit time was this 1.5 times 10 to the 8 joules, or excuse me, watts. That's your QC divided by time. And then your C is the heat capacity of water, which is 4190 joules per kilogram Kelvin. And then your delta T is a half Kelvin, which is the same as a half degree C. Plugging that into a calculator, you might get 7.16 times 10 to the 5 kilograms per second. Okay, I'm gonna attempt to stay on the same board for the next problem. So, no, I really don't think it's worth it. I'm just gonna do a whole new board. So for part E, you want to get the entropy. What exactly do they ask? Entropy of the river. So you have something that's changing its temperature and you ask what the entropy is. You want to use this formula based on the fact that it's Q is MC T, delta T. But I know this is somewhere in the chapter. So you want to use MC T2 over T1, where T2 is your, sorry, what was the temperature? It was 18.5, not 80, 18.5. And then this is your 18 degrees C. But you also want to add 273 to get this whole thing kind of in units of Kelvin. That's a 3, sorry. So yeah, so that's what you want to plug in there, the mass. And then you want to divide both sides by time again, and then to get a rate. So then the mass per unit time, you want to use the number from the previous problem. And then your C is your 4190 joules per kilogram Kelvin. And I got 52 times 10 to the 5 joules per Kelvin.